Hi, in this lecture video, I want to describe using, another way to use the wave function, or actually another way to ask the wave function questions. And the answers to these questions are referred to as expectation values. This is one way to connect the wave function to the physics of an experiment, to what might be the outcomes of experiments. Right? This is how the wave function would represent the real world, right? The real thing happening in nature, right? Which you express data about with distances and momentums and kinetic energies, right? So this is how to connect the wave function of quantum mechanics to the reality of making observations. So let me say that. This is how we connect the wave function of quantum mechanics to observations in the real world, right, of experiments. No experiment is ever going to show you psi directly. Experiments are only ever going to give you outcomes, right? You're going to measure values, and somehow psi makes predictions of those values. This is the point of the lecture today, is these expectation values. So for fun, I'm going to practice with our toy model that I introduced in the previous lecture. So let me rewrite this toy model. And our toy model looked like this. So psi was a function of x and t, and it was piecewise defined. It had, and I'm going ahead and putting in what we discovered as the normalization constant. It was 4 over 5L inside of a square root, multiplying e to the minus I e t over h bar. And this was for x values from 0 to L. And then there was negative 1 over 2, 4 over 5L square root, e to the minus I e t over h bar. And this was appropriate, or the piecewise defined over the interval minus L up to 0. And then the wave function actually had the value 0 for x being other places, right? So this was the piecewise definition. So somehow, right, psi star psi dx, this right here is probability, right? This is a probability density. Psi star psi is the density, but if I multiply a density times a distance, then I get probability, not density, right? So as an aside, one thing you can do with what are called probability distributions, so I'll call them distros, right? Probability distros. If you have a probability distribution, that means that the probability is distributed over different values of x, right? Where x is the sort of various answers or various outcomes. And let's say that this actually is a probability density, so that we have to multiply by a dx to get a probability. So we know that if I integrate this over all possible outcomes x, it's supposed to add up to 1, because the probability of any of the possibilities happening is 1. So the way I can use this, though, is I can say, well, I wonder what, if I was to do many measurements of x, and by that I mean millions and millions of separate measurements of x, I wonder what the average value of x is. So there's a special way to symbolize the average value of x. It's often written this way. This right here is referred to as the expectation value, except for this kind of is a misnomer, because it's not necessarily the value that you would expect from any particular measurement. So I want to type this out. This expectation value is not what you should expect as the outcome of any particular single experiment. The expectation value represents the average of the result x from many separate experiments, right? I'm going to include it where each experiment is where the outcomes of each experiment is defined by the same probability distribution. This is important. It's something that you should dwell on. You should dwell on the point I'm trying to bring up with these comments. These are important comments, right? It's got to do with interpreting the answers you can ask of the wave function. So this is something that you can ask the wave function. You can ask it for an expectation value of some measurable quantity. And it will return for you, if you ask it this way, not the result of any particular experiment, right, or of any particular single measurement of something, but it will tell you the average value you would expect to have after doing the particular measurement hundreds of millions of times, is the idea. So it's truly a statistical statement. It's not telling you what you're going to get when you do the experiment once. Okay, so let me show you how you use it, though. So the expectation value of x, or the average value of x, is defined by doing the following thing. If you have this probability density, then all you got to do in order to measure the average value of x is to integrate or add up all of the values of x, all of the possible values of x, times their respective probabilities for being the outcome of an experiment. And you do this over all possible x values, all possible outcomes of the experiment. So if we want to use this in quantum mechanics, we could say, what's the average value of the position of a particle that you would measure when you do an experiment? And the way you would get it is you go, in our particular case, all the possible x values are from negative infinity to infinity. The x value, or the function x, we put it in, but actually we do kind of a strange thing. We put it in between, we put psi star first, psi second, so we put it in the middle. It's not off to the side, but actually sandwiched in the middle. And we finish off by, describing the small intervals. So this right here is called the average value of x. So sometimes this is written as x sub average, right? And in fact, actually, if you want to know the expectation value of any function of x, this is still the way you do it. You sandwich that function of x in between psi star and psi and finish out the integral. So a really interesting, so this is how to ask certain questions. The thing you want to ask, you can get the average value if you sandwich it in between psi star and psi. There are some questions, though, some physical quantities that are represented by the derivative operation, and in particular, the momentum. If you want to know the average value of the momentum in the x direction, so, in this toy model, I have a wave function that only tells me about x direction stuff. And so supposedly this is a physical model of a physical little particle, and that particle has motion, right? So this system should have momentum. And this system's momentum is represented by what's referred to as an operator. It's minus IH bar d by dx. And the way that you use it is you say that I can ask the wave function for the average value of the momentum, and it's going to be equal to the integral over all possible, so this is strange, it's actually over all possible x values of psi star, remember, is a function of x and t, and then you sandwich our operation in between psi star and psi. And then you finish over the, by adding it up, multiplied over the small interval dx's. So the thing is, though, is this operation is imagined to only act on psi, and psi star is always tacked on the left-hand side, and it's not operated on, right? So this derivative is going to hit the psi over here. So in the previous video, or actually, let me point out something for this example. It's actually not very physical, and let me show you why. Because remember, I drew a picture of psi versus x, and the way it looked is I had a rectangle here and a rectangle here, right? And it was 0 everywhere else. So d by dx on psi, right? So minus IH bar is the rest of the operation, you just, like, all this means is you multiply the minus IH bar. And by the way, the complex conjugate is only on psi. So the complex conjugate is not hitting the minus IH bar in here. That's kind of like an afterthought. So the minus IH bar d by dx is an afterthought operation that you can do after knowledge of psi already, right? But anyways, the derivative is not well defined in this piecewise defined thing, because whenever you have, right, because remember the derivative is the slope. So the slope here, that's well defined. The slope is 0. The point is if you look at the wave function, there are long parts of the intervals over which the wave function is defined that are actually independent of x. But actually there is this dependence on x because it's piecewise defined, and the transitions between the piecewise definitions include slopes that are infinity, right? Here's an infinite slope, right? I've got a rise over a 0 run, right? So that's an infinite slope, an infinite slope. So this toy model is not a good example to try to use the momentum operator. But you'll have homework problems, which are good example, right? So do the homework so that you can practice this.